All right, thanks for coming for my presentation. Today I'll be talking about fearless concurrency in Rust, which is the term they use actually. And I will be talking about how Rust manages its memory, different concurrency models in Rust, as well as we'll go through some code demos to show you how this works. All right, so what is Rust? You might have heard of this language before. It's apparently the most loved language. You can see this red circle is the percentage of developers who've used Rust who want to keep using it next year. That's more than 80%. It's a lot of people and way more than most of the other languages on this board. It's also recommended by the White House as a language that's close to the kernel, deterministic, doesn't have a garbage collector, and yet is memory safe. So how does it achieve that, right? What's so great about it, right? Well, we've heard some things about why it's so great. But to understand why it is so good, we're going to talk about some memory management trade-offs first. So you might know there's two main kinds. There's manual and automatic memory management. So with manual memory management, memory errors are possible because of human mistakes, because you might write an algorithm that's not fully correct when parallel. And you see this in C, in C++ as well. And there's also a huge class of languages that are automatically garbage collected or reference counted. And these are generally memory safe because you don't manage the memory yourself. The garbage collector or the reference counter does that for you. But the problem is that garbage collector, when they pause and do garbage collection, that affects your performance, and it can happen at non-deterministic times. It's kind of like the OS scheduler. Kind of anything could happen, and you can't really predict it. So that's not great for low-level systems where latency is an issue. The question is, can we have memory safety without a garbage collector? And I'm saying that with Rust, you get this. Enter the Rust borrow checker. So now we talk about ownership and borrow checking and what that actually means. So you might have heard of these terms before. You might have heard they're kind of scary. So I'll try to explain it today. But the idea is that ownership and borrow checking gives you memory safety. And that's kind of a bold claim. So what's ownership? It has two main rules. The first is that every value, every variable has exactly one owner. Not zero, not more than one, exactly one, right? And when the owner goes out of scope, the value is dropped. So um, that's the first part of ownership. The second part of ownership is called move semantics. This happens so basically when you assign a value to a new binding. So if you assign some old binding to a new binding, the old binding becomes no longer valid. It's not bound to any value, so you cannot use it anymore, and the compiler will enforce this. This usually happens when you're passing parameters to a function because a parameter is basically a binding, and it happens when you're returning values from a function as well. So these are actually patterns that are used in C++ as well, both RAII and move semantics. So Rust is not like unique in coming up with this, but it does use these great features and combines them into like a well-designed language. So here's an example of how ownership works, right? Let's say you have a vector of numbers 1 and 2, and you have a binding, myvec, that owns it. So it's pointing to it. But you want to pass this to another function called modify that takes a vector as a parameter. What happens when you do this? Well, ownership is transferred to the binding v in the function modify, right? This this situation is not possible. Um, and the compiler specifically prevents this because of the single ownership principle. And you should think about why this is important, right? This is not allowed, right? Why is it not allowed? Well, if you have two things which own the same piece of data, what could happen is that one of your pieces of data, right, like v, for instance, could go out of scope and try to free vector, RAII, as you might know. If v goes out of scope, it will free anything that's within its scope. And if vector is owned by v, then it might try to free vector, but myvec is still pointing at it. So now you get like a double free. And when myvec goes to access vector, it's going to be invalid memory. So this avoids that situation. Next up, we have borrow checking. And kind of in a nutshell, borrow checking is basically a read-write lock pattern that is statically checked at compile time. So there's no real read-write lock, but it is just a rule enforced by the compiler. The unique thing here is that it's on every single value in the language, every value without exception, unless you mark it as mutable. So as you might imagine, this causes like quite a bit of pain. But finding the borrow checker, as a lot of Rust developers do, helps you write correct programs. So here are some modes you can borrow a variable. So the first way of borrowing a reference is to borrow it mutably. This happens usually when you have a writer that wants to modify the value. You need a mutable reference to mutate it. The other way is to borrow an immutable reference. And this is usually when you want to just read the value. And here you can have multiple readers because they can affect each other because the value is immutable. What's not allowed is having both readers and writers, because what might happen is that your reader might read a value like 4, and your writer might modify it to become like 6, right? And now your reader reads it again, and it sees that the value is now 6 instead of 4. So clearly it's not immutable, and that kind of violates the semantics of that. So this is not allowed. And like not allowing this actually is pretty nice because you know that immutable references cannot, the underlying data cannot change. So everything in Rust gets a read-write lock, no matter whether you like it or not, and you just have to abide by the rules that's enforced by the borrow checker so that you write correct parallel programs. So this is actually good because you get these kinds of compile time checks for zero overhead because there's no actual lock involved. It's just a set of rules checked by the compiler. So you get this without any performance hit, and that's great. So put together, both ownership and borrow checking prevent these whole classes of like memory errors, including many but not all data races, because it's not theoretically possible to prevent every single data race. It's equivalent to the halting problem. Um, and it also prevents unreproducible reads, like we mentioned earlier. Okay, so we know all this about the Rust memory model and how it handles memory safely. But what does this have to do with concurrency, right? So Rust has two main concurrency models. The first one is coroutines, usually used as async await, which is a kind of a pattern of using coroutines. So these are great for blocking operations like I/O operations or network operations. You see this in JavaScript or C Sharp, and it's pretty similar. And the other one is kind of like your standard threads, like in C++, and these are great for parallel algorithms. So we'll go quickly over what coroutines are and how async await works. So in this case, we have a bunch of blocking operations, fetching URL, getting data out of it. And because they take time, they take lots of CPU cycles, we want to await them and go do something else first. And when they're ready, we come back. And how this is actually implemented is that the compiler, there's a lot of work put into it to turn this into a state machine. These are the enums that show like the different states that are possible. It goes from one to the next to the next to the next. There's a lot of code underneath for the state transitions and the actual behavior, but this is basically how it works. And this is pretty similar in other languages as well. But what's maybe more relevant for parallel programming is threading. And one big problem in threading is how we want to communicate between threads, right? And there's two main ways. The first one is through shared state. You allocate someplace on a heap and you wrap it with a mutex so you can have thread safe access and all the usual suspects. In this case, the borrow checker actually prevents certain kinds of bugs, and we'll see this in a bit in the coding part. And the other way is message passing. So the creator of Go kind of coined this idiom that says don't communicate by sharing memory because it's error prone. Share memory by communicating. And we'll see a way in which Rust does this with channels, kind of similar to Go. All right, time to look at the code. All right, onto the code. If you want to follow along, you can find it at this link on my GitHub account. And yeah, you can take a close look at the code there. But let's jump into it. Let's look at a pretty basic problem. We want to sum up numbers from 0 to 10,000 and check that the result is correct. So that's what this does. And make vec_sum is our custom sum implementation. Obviously, this is kind of silly and a bit, it's not very idiomatic in Rust because this is very procedural code, which Rust tries to avoid. But basically, this is a sequential algorithm. We're just going through it and getting the total out of it and just returning it and checking it. So you should see that this is pretty straightforward and should be correct. So we're going to run it, and just to show that there's no race condition, yeah, so it passes. We run it a few times. And now we want to parallelize it, right? So let's see how we can parallelize this in C++. So in C++, what we could do is we could spawn threads, right? Threads, they call a worker function, and basically it gets a slice, a chunk of the vector that's adding this vector over here from 0 to 10,000, and it just adds it to a shared variable total, which are passing by reference into the worker function. You kind of see already that there's going to be a race condition here, and we're just going to demonstrate that. So shared state race. So yeah, it's already failing, right? It should pass sometimes, but with a big enough set of numbers and enough threads, we're going to get a race condition here. So how do we fix it? It's not that hard. We can use a mutex, right? Just lock it. And after we lock it, we shouldn't have a race condition anymore. So I'm going to clear this. I'm going to run this a few times, and so far, no incorrect results, so should be good, right? The point here isn't to tell you how to use the mutex, you already know that. The point is that C++ allows you to make an error like this, and it will compile it without complaining. And you won't even know it's wrong until you actually run it and you realize it's a race condition, right? Um, Obviously, you wouldn't write this code exactly like that with modern C++. I would argue that C++23, it's kind of has a lot of the same features as Rust. They kind of influence each other. But as is C++ like 11, people still write code like this, and it's wrong without them even like realizing that it's wrong. So let's try to do the same thing in Rust. Let's see what happens when you try to do this in Rust, right? So here, there's a bunch of Rust stuff. You don't have to worry about that. But the idea is there's some shared variable here called total, and we are basically doing the same thing with spawning threads here, thread spawn, and we are adding num to total, right? So we're basically doing the same code, and you'll see that if we try to do this, right? So this is shared state race. Same idea. We're going to try to cargo run, and it doesn't compile. It doesn't compile. It complains we cannot borrow total as mutable more than once. We have multiple mutable references here, and that's not allowed, like we talked about earlier. How does that happen? Well, total is here, and we are spawning multiple threads that all have a reference to total, right? And that is not allowed. And in fact, the borrow checker tells you as much, that this is not allowed, and it actually prevents you from having a race condition at compile time. And that's the power of Rust. It will tell you when things will go wrong. It will not catch every single kind of race condition, but it will catch a lot of them, and it's catching this one. So it forces you to think, okay, maybe I should do things differently. One way to do it is to do the Rust version of the mutex. We have a read-write lock here, and an arc is basically a pointer. You can think of it that way. And with a read-write lock, right, we are getting a write lock here. You will see that not only does the code compile, it also, cargo run, gives us the correct result. So you see that in Rust, often if your code compiles and you didn't use unsafe blocks, which are a more advanced feature, you should get correct results usually, and that's really nice. So it stops you from shooting yourself in the foot, basically, and that's a nice safety feature. Let's actually go one step further and try and even, I think, a better implementation of this, which is with message passing. And that's a pretty an idiomatic Rust way of doing this. Basically, instead of having a shared variable, a shared state, you have a channel. So this is a multi-producer single consumer channel. And so you have multiple threads producing a total value, a local total value, and a single consumer, which is the main, that just adds them up together. The crucial thing here is that this channel is thread safe. Smart people have figured out how to do this in a thread safe manner, and we get to just use it. So the idea is we compute a local total, we send it to the sender channel, and then the main thread, so this is the main thread, is going to aggregate all of them together and return it. And you'll see that this is also a correct implementation. Let's clear this a bit. Run, 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 run. Looks good. And this is the other way of doing concurrency with message passing. I think often this is cleaner and less error prone. So this is a great option that Rust offers. So yeah, you'll see that through these examples, hopefully you see that Rust checks things which other compilers like G++ might not check, might not be able to catch because of the strict rules that the borrow checker puts you through. So you fight a borrow checker, but you come out of the other side with the correct program. And I think that's the power of Rust. And I hope you try Rust. I really like the language. I think it's a great, well-designed language. And I hope you try writing some parallel programs because it's great for that as well. And yeah, thanks for coming from my presentation. I hope you learned something. And yeah, goodbye.